So, welcome to our discussion of feed fractions. Normally, I do this on the whiteboard and we'd be there to bounce things back and forth. So, we're going to lose that interaction, but I'm guessing that this will be a little bit more clear. I really took some time to create slides. So this is a slide you've all, or at least concepts you've seen before, mine are not a specific slide. We take the feed, we split it into water and dry matter. That's our first nutrient. Then we take the dry matter and we divide that into carbohydrates, protein, fat, minerals, and vitamins. Those are our 6 nutrients there. So if we take each one and break them down more definitively, more into smaller fractions, we'll get the rest of the slides here. So if we take the carbohydrates, we're going to divide them into NDF and non-fiber carbohydrate. So neutral detergent fiber is our cell wall. We talk about hemicellulose, cellulose, and lignin all kind of working together to create this sheet that surrounds the plant cell. It's a very complex carbohydrate. There's an ability to stretch until it gets older, and we bring in the lignin, and that hardens things up, makes things tough, makes things more rigid. And as we dealt with like straw and stuff, it tends to break when you bend it, as opposed to young grass, which is going to be much more flexible, a lot less lignin. So when we go with NDF into the rumen, and we'll be talking a lot more about this, you're going to think about digestible or fermentable. People will say, well, is it digestible NDF? But really what's happening is the microbes are fermenting it in the rumen. Their microbes are digesting it in the rumen. So you have to be able to make that mental leap going back and forth that fermentation is digestion when most people are talking about it. And then there's the undigestible or unfermentable components of NDF. No matter how long that NDF would stay in the rumen, it would never become available. So you have the stuff that's available to the animal, the stuff that's not available to the animal. We also think about our NDF. We have to think about our physically effective NDF, its ability to stimulate chewing. And there are several factors that help determine how much it stimulates chewing. We usually think about particle size, but we can think about toughness or fragility. The more lignin we have, the more rigid it is, the more it's going to resist breakdown with the teeth going through. Non-fiber carbohydrate, NFC. We have our pectin, which will be sort of associated with the cell wall in some levels, not usually inside, and then the carbohydrates that we're going to find what we'd consider maybe cell contents. We're going to have sugar, starch, fructans that are going to be there when the animal or the plant is growing, living, respiring, storing energy for the future. So these are simple sugars. We take those sugars together and put them together in chains. We have the starches and fructosans. They are the storage carbohydrates for later. If we put the cell contents into a fermentation, we're going to convert those sugars, convert some of that starch, some of that fructosan to lactate VFAs that are going to help preserve the forage. Hopefully, it's mostly lactate. VFAs aren't nearly as acid generating as lactate. Lactate is 10 times, lactic acid is 10 times stronger in acid than the VFAs, the volatile fatty acids. Protein. When we think about protein today, this is usually where we are. In the future, things are going to change a lot, probably in your lifetime. So we're still dealing with crude protein. We measure the nitrogen, we multiply it by 6.25 for most of our feeds. If you know you're dealing with just milk protein, you might, I think the factor is 6.32. So if you have a specific type of protein, you can get that correction factor. for that type of protein, but this is a good average across all the feedstuffs. And then you have your fractions that you're going to look for or balance with as we move forward. So you've got non-protein nitrogen, NPN. That's going to come in the form of urea and ammonia. Those are, ureas to ammonia stuck together basically. Nitrates and nitrites are going to measure as that nitrogen available. We're going to have amino acids and peptides, which are the building blocks of true protein, but they're going to be very soluble, very available. They're not long enough to be called a protein, and that gets a little iffy. How long does a peptide have to be before it becomes a protein? You have to ask that question. There's also a number of organic molecules that might end up in this fraction, like vitamins and maybe some unesterified lignin components that might end up in this fraction that have nitrogen as well. Not usually a large amount. We're usually talking about ammonia and urea as the majority. Hopefully, we have lots of amino acids, very little of this, very little of that. Soluble protein, we mentioned that before. That's going to be a combination of NPN. Most of this is soluble in a buffer solution. It's basically artificial spit. Soak for an hour, measure how much goes into solution. You're all going to have some true protein. This is usually considered very available protein. The microbes get a hold of it right away. Soluble protein is expected to be dissipated in the rumen, and we're looking at minutes time. It's usually not around for an hour when it comes in with the feed stuff. You've got true protein, and there are a number of different proteins there. There's some that are very easily accessible to the microbes and some that are more resistant. They don't go into solution as well. They are not as accessible to microbial proteases, the enzymes that break down proteins. So you're going to have a range of proteins, and they're sorted by rate when we're balancing rations. The fast proteins are usually called the B1 fraction, and then we got B2, B3 are the slower fractions. Then we'll have bound protein, unavailable protein, acid detergent, insoluble nitrogen that's not available to the cow. We can multiply these by 6.25 to get bound quote unquote protein, the nitrogen associated with this stuff times 6.25 gives us a crude protein equivalent. You're also going to have, and this is something we didn't talk about in 100, but there's going to be cell wall proteins. Not a lot, but there's going to be some. And these proteins are usually in that B fraction of true protein up here. So you're also going to have the lignin, which is going to be in the bound area. So you're going to take the cell wall nitrogen, and some of it's going to be bound, some of it's going to be very resistant protein. So that's something we didn't mention in 100 because we didn't want to confuse you. So that's sort of where the state of protein measurement is. The future, as we get more and more research, more and more computer power, we're going to be able to start to balance, we hope, our cows on an amino acid level. So what essential amino acids go and non-essential go into the cow that are in the feed fractions? What happens to them in the rumen? How do they come out? So that's going to require a lot of research to quantify what's in the feedstuffs. It's a very expensive thing to do, but as computer power comes down, we'll be able to measure those in the future. We also have to figure out what happens in the rumen, and that requires a lot of computer power. We're talking about probabilistic models, mechanistic models that deal with probability, and if 50% goes here, 50% of the time goes there, all that stuff. Certainly chickens, pigs, all the simple stomach animals balance on an amino acid level. I would say that's going to be the future for protein. Fats. We're going to divide these more or less into available and unavailable. Available, we're usually looking at something related to fatty acids. So we got triglycerides, a glycerol molecule with 3 fatty acids on it, phospholipids, the cell membranes of all the feed tissue, plant tissue, all have cell membranes. They're all phospholipids, so they are going to be available to the animal. So recycling those. And then free fatty acids. The fatty acids, 3 here, 2 here, and individual ones there, are going to vary in the number or in length or the number of carbons in the chain. And you've got the unsaturatedness or the number of double bonds. The more unsaturated it is, the more lower the melting point, boil or liquid point. So we knew that our plant fatty acids tend to be unsaturated. Our animal or ruminant ones tend to be saturated. So most of what a cow eats is going to fall in this unsaturated, and what really varies is the number and placement of those double bonds. If you go through and do an ether extract, you're also going to pull out waxes and chitin, cutin. These are the waxes that kind of protect the surface of the plant from drying out. These are generally not digestible and tend to pass through the cow's body without being being absorbed and being part of what the animal can use for digestible. When we analyze our fats, most of the time it's about ether extract. That's a crude measurement of total fat. How much fat is there? You're going to get all this stuff here, and this stuff here is going to end up in that. A lot of places are going to total fatty acids, so measuring the amount of fatty acids so we can balance our fatty acid load to make sure we don't get milk fat depression, make sure we don't overdo things. When all else fails, you can take ether extract percent, subtract 1, and that gives us our estimate of total fatty acids for that feed stuff. So if you're looking at a forage, say haylage, usually 3% fat, we subtract 1, we expect all the fatty acids in that 3% to account for 2/3 or 2% of the total dry matter. So the rest is the glycerol or the phosphorus, different things that are attached to it, stuff that's mixed in are not going to be fatty acids. So that's where we pull out the glycerol, the phosphorus, the glycerol, the waxes and stuff is accounted for in that 1%. If you want to get down to individual fatty acids, and there are occasions where a research group might be interested in those, most farms never get to those, at least not yet. It's an expensive and tedious thing. Hopefully things get sorted out. As a reminder, we can also classify our fats by source. We can either divide them up as basal, what's in the basal diet, what we add from our grains, and then what we may add is megalac or megalac knockoff, our protected fats, our ruminant inert fats moving through. We also could break it down into vegetable. Are they plant-based? Is the fat coming from oil seeds? Is it coming from animals as tallow or different projects like energy boosters processed there? Do we have manufactured fats like megalac and the knockoffs thereof? So depending on what you're looking at, you can divide this way or that way. Minerals, pretty straightforward. We got our macro minerals, our micro minerals. We can measure the questionable, but there really doesn't. We're never going to balance for them. We've got more than enough questionable, more than enough to satisfy any potential requirement, and the ones we have to worry about either, and this is usually any mineral in excess can become toxic. We think about lead and uranium, plutonium, those things in certain contaminated areas. And then if we get almost any of these micro minerals in too much, they become toxic as well. So we're looking for our minerals, we're looking for the range, too little and we're undergrowing, too much and we're toxic. We had that curve in 100 where we have deficient, optimum, and then toxic destroys our animal response. So our 7 here are constant, depending on which list you look at for micro minerals. Different ones are included depending on who's writing the thing, who's not. Nickel is not one we've talked about, but some people say it's required. You're never going to supplement for it. There's enough contamination in feedstuffs to make sure that gets taken care of, but it appears in some studies that it might be useful to the animal. We're looking at methods to measure minerals. We've got crude ash, 5 hours at 500 degrees C. We blow off all the organic components, anything taking a carbon, we're left with minerals. Basically, all these will end up in the beaker after everything is burned off. We can measure those by atomic absorption or inductively coupled plasma spectroscopy. So either one of those gets the job done. I think most places use this now. This can be very tedious. I've spent a lot of time with that. It seems most of the bigger one get through have moved in this direction. Minerals. We divide our minerals into two categories: fat soluble, water soluble. And we pretty much never analyze for them in a practical setting. Analysis is expensive and complicated. We supplement A, D, and E. Those are the ones that are going to usually be limited in our production systems. K, B, C's, choline are generally produced by a healthy rumen, and we don't need to supplement them. There are situations where we talk about niacin or choline that maybe the early lactation animal will respond to additional levels beyond what's in the rumen. If we got an animal out in the sunlight, D, and on green grass, A and E, we may not have to supplement them either. If you're looking at beef cattle on pasture in the summertime, generally those blocks out there only have minerals, they don't need vitamins. So, but our confined animals, we usually, on preserved forages, A, D, and E are what we usually supplement. I think that's it. We're coming back to a summary slide here. So we've talked about our fractions. We're going to take the carbohydrate, we're going to break it apart into NDF and NFC, and we're going to talk about that over the next week or so. Protein, non-protein nitrogen, true protein, bound protein. We hope that most of what we feed the animals has true protein for the nitrogen sources, but we know that NPN sources can be cheap, and we need a certain amount of NPM to make the rumen work optimally. We need to have the microbes take that nitrogen, turn it into useful protein that the cow can use. We have the fat, triglycerides, phospholipids, free fatty acids, and then unavailable sources. We hope, again, that the majority of the fat falls into that category, but we can't have too much or we're going to overdo it. So that 6% of free fat, anything above that needs to be protected. Dividing our minerals into macro, micro, questionable, and toxic, and then our vitamins, fat, and water soluble. So that's a review on some level, but at the same time, I think we've gone a little bit more depth than we did before.